Hi, everyone. Welcome to Fractional Excitations, a podcast from the Tafti Lab at Boston College. The purpose of this podcast is to talk about the human aspects of graduate research experience. Every time one of our students in the Tafti Lab publishes a scientific article, we organize and record the podcast to discuss the challenges they faced and the triumphs they achieved. Today's podcast is about a recent publication from our lab, from the Tafti lab, on the chiral magnetic fluctuations in rare earth manganese tin materials. This was a work done by my graduate student, Kyle Fruhling, who's with us here in the studio. Also, two graduate students, Enrique Gonzalez and Sudarman Balguri, are with us helping recording this podcast. My name is Fazil Tafti, and welcome to Fractional Excitations. Kyle, congratulations
Thank you.
on the publications of your very nice work in the magnetic state of erbium manganese 6 You published a recent article in Physical Review Materials. It appeared as the editor's choice on the journal. The title of this work is Topological Hall Effect Induced by Chiral Fluctuations in Erbium Manganese 6 Tin 6. You and I know that it took a long time to develop this work from the concept to the material synthesis and growth of good quality and large crystals, to performing magnetization experiments, to performing transport measurements and neutron scattering experiments. And ultimately, it resulted in this wonderful publication, which was recognized by the editors of Physical Review Materials as an editor's choice. This is usually an honorary position for a publication in any journal when an editor selects a paper as the special appearance in that edition of their journal. And your work was selected as the editor's choice. So let's go to the day when you heard the news that your paper was accepted finally for publication after months of working on this project, battling with the referees, improving the results, changing the write-up, all the failures and successes that you face in this project, you finally heard the great news of your paper being accepted. Tell us, how did that feel and what did you do?
Well, mostly I just felt relief because from when I started 4 years ago, I've always been working on these rare earth manganese 6 materials, and those materials have a lot of people working on them. And erbium specifically, when we were looking at doing neutron diffraction on it, we knew there were other groups doing it, and I spent most of these years just a little bit in the back of my mind thinking I was going to wake up one day and find that someone had scooped us. So it was really just relief, just a great relief to not have to worry about that, to have something out there and published and accepted. And then I just went and celebrated. I grabbed a cigar from a place near my hotel I was staying at the time and had a walk in the park, and it felt good.
That's a great way to celebrate. And maybe for our audience, you can tell us where you were, in fact, when you heard the news.
At the time, I was doing an internship at Air Force Research Labs in Dayton, Ohio, which doesn't, obviously this paper was accepted, so it doesn't come into how this paper was, but it was a great opportunity to get to meet some scientists and learn some new techniques that I wasn't familiar with beforehand.
Now, maybe to that note, I can explain something to our audience. The way that graduate research is performed in, at least in American universities, is usually through funding agencies where PIs or principal investigators, such as myself, have a general idea for a project. They propose it to, for example, National Science Foundation, in your case, in the case of Kyle's project, and they receive funding to investigate a specific physical system. then that funding would be used to pay for the salary of students such as Kyle, and it would pay for the materials that they purchase or travels that they make. And part of this effort is connected strongly to National Science Foundation in the sense that the taxpayers' money is being used for the education of the next generation of young scientists. In that, I always feel a great responsibility, both because the government is funding us to perform good science and because there is a responsibility in training the young next generation of scientists. So I tell you that in your case, it's just my own feeling that I'm really proud of the work you've done and very happy with the work I've done in having you as a graduate student working in my lab. Kyle has been very responsible for his project. He's also an excellent experimentalist. The stuff he did were very challenging in this project. It was not an easy project from the design of the material to growing good crystals of the material to performing extensive, I would say almost exquisite experiments. This was no easy task. It was a national collaboration. In fact, it was an international collaboration. So the graduate student was at the center of all of this, working with professional scientists from different countries. And I think you did a really great job in withstanding the pressure and doing it responsibly. Maybe tell us a bit about the challenges of this project in terms of both in terms of coordinating this international effort, working with other scientists, and maybe in the end tell us about how it formed you as a young, up and coming, slowly becoming independent scientist.
Well, I mean, there were plenty of challenges along the way. By the time we were making erbium manganese tin, we had kind of worked out a basic recipe for rare earth manganese tin because we had already made terbium and holmium versions of this material. We did some slight tweaking with the temperatures and the ratios to get it to be the best we could. There were some impurity phases that exist, I think manganese tin being one of them. But we got it to be pretty good pretty quick. The big issue with growing the crystal that we experienced was when we were preparing crystals for neutron diffraction. They had to be a certain size, and we could get crystals that large, but they would almost always grow into each other and be twinned, which complicates everything massively. So we just kept growing more crystals a bunch of different ways until we finally got some good ones. And then I found out later that they were maybe too big and we had overshot the optimal size. So we know for the future there is an optimal size. But we got those together. And then the real big complication was as we sent these out, when we initially were exploring this, we were kind of just exploring it. These materials, especially terbium manganese tin, they're all topological, and that one was a great topological insulator. So it's had a lot of research done on it, and we were just kind of exploring these materials and seeing what we could find and where we could get in to contribute to this. And while we were doing that, that was our initial um, we were initially submitting our proposal for neutron time. That was what we were just trying to investigate what the magnetic state was. And as we were investigating it, we found that there was this antiferromagnetic and ferromagnetic phase, and this antiferromagnetic phase was kind of this dome. At certain temperatures, it required a higher field to get it to flip from this antiferromagnetic to ferromagnetic phase. And we also found this paper where they found a topological Hall effect in it. And we tried to recreate that paper, reproduce the results, and it took us a ton of tries, and we didn't reproduce it until we had already sent the crystal for neutron time. So we had to kind of calibrate our neutron experiment as we were doing it to figure out what would show us what we wanted. And even as it was, by the time we really figured out what we were looking for in the topological Hall effect, arguably our smoking gun neutron data that we wanted, we just couldn't get with the time we had. So we that added in a complication because we had to really make a good argument for why we thought that this topological Hall effect that was seen in this previous paper and that we had seen kind of came from this chiral fluctuations forming this transverse conical spiral, which is really what the central idea of the paper is that this topological Hall effect doesn't come from skyrmions, but it comes from this kind of transverse conical spiral structure to the spins. So we had to consult with a lot of scientists, theorists, and then also our neutron people that we were working with to really work out, could this argument make sense, and are we on the right path? So those were all kind of complicated things, but all kind of led to where we were going and helped us really explore it and focus on what we had found and how we could describe it.
In any scientific project, especially when a PI such as myself works with a PhD student such as Kyle, there are some memorable moments. And I can think of a few memorable moments throughout this project. Mostly they're scientifically memorable moments. I would tell my own memorable moments, and I would love to hear yours. One of the breakthrough moments, as I remember, was when you grew many different crystals, and we always got some kind of impurity in them. And we were changing the growth conditions. And one day I remember you just sat down and summarized everything you did for the growth of all these different samples and and showed it to me on your lab book, if I remember correctly. I even remember that you wrote this with a pencil, not with a pen, if I remember correctly. And and I remember this because I really enjoyed that moment, because in a sense I felt that you are kind of growing really into a critical thinker, and in the sense that you can now analyze everything you did, and you had a proposal about how you're gonna tackle the problem of getting rid of the impurity phase. For me, it was a really interesting and pleasant moment, because I could see how you just collected all of your efforts in making the crystal and then coming up with an idea as to how to clean it and make the single phase and large crystals. So that was a nice moment for me. The other moment I remember was when we first were discussing the figure that became kind of the heart, the central result of this work. It was basically a phase diagram, but it was not just a regular phase diagram. It was a phase diagram where you had to interpolate using color scheme in a Python code from one phase to another, and that interpolation very nicely revealed this region of magnetic fluctuations or chiral fluctuations. And I remember discussing this on the board with you and another graduate students who was collaborating with you, Elena Streeter, uh, and we discussed this concept. And I remember when I first saw the figures that you made together, it was really impressive for me, because I just sketched something on the board, but it was just wonderful to see how you two played with the code and made that beautiful first phase diagram. That was another great moment for me. And the third one was, in fact, when, as you said, we were running the neutron scattering experiment. I was, in fact, in a meeting at the Air Force Lab in Dayton, Ohio, discussing some other projects from the Air Force Research Lab. It was sort of a funding meeting, but it was through that meeting where we were actually running the neutron scattering experiment. And I had to skip here and there, skip a little bit of time, maybe during coffee break, or sometimes maybe I had to miss one talk because you were running the neutron scattering time. It was happening in Switzerland, and I had to come and talk to you and plan for the next step. And as you said, you were still getting data that was very helpful to plan for the experiment at that time. And so it was this constant sort of back and forth. I was sitting there, but I really wanted to go what's going on experimentally. And I would just sneak out, talk to you on Zoom, and then go back in my meeting. And this discussion even continued to some of my flights. I was connecting flights, and I was constantly on Slack, like talking with the two of you about what's going on experimentally. So for me, that was really, it was stressful, but it was a lot of fun at the same time. I really cherish those moments. How about you? Could you tell us some of the moments that you remember from this experience?
I kind of feel like I shared most of the ones I really remember from the challenges, but one thing I really remember is when we first met with our collaborator, Igor Mazin.
Mm-hmm.
Mazin?
Mazin, yeah.
Mazin, yeah. Um, and we were showing him our results, and we're like, as you can see, here's one phase, here's another phase, and here's the transition. And he's just like, I think that transition's another phase. It was like, which just completely changed how we looked at the project and what we were looking at. And like, oh, maybe this topological Hall effect is not necessarily like just a transition. It is its own magnetic phase that we should be looking at. These magnetic fluctuations can lead to an actual particular structure to these spins that leads to this topological Hall effect. So that was really cool. Just kind of having one discussion and having the entire project not really change. We didn't have to do a whole lot extra after that, but just how we were looking at it completely changing in a couple of minutes.
That's absolutely true. And that collaboration, in fact, with the theorist Igor Mazin was a very pivotal uh, piece of work in the whole project. It really shaped our thinking about your findings. It's absolutely right. Shouts out to Igor
Mm-hmm.
for his wonderful ideas and helping with this project. Well, let's flash back. Now, we talked about your project, memorable moments you had, challenges you faced throughout this, and of course, the triumph of having your work published as editor's suggestion in Physical Review Materials. Let's go back to when you started to think about becoming a physicist. How did you, in the first place, how did you even enter this world of physics and eventually became a PhD candidate and you're on your way to becoming a doctoral physicist, basically?
Um, a lot of it is just kind of defaulted into being here because I just liked science as a kid, as I'm certain many of us did. You just grow up as a kid, kind of like in science. You like dinosaurs, you like space. And then in high school, I took physics and astronomy in the same semester. And my astronomy class was with one of my favorite science teachers at my high school. And I also really liked my physics teacher, and they made it really interesting and fun. So then I became an astrophysics major in undergrad. I just kind of went in not really knowing what I wanted to do, but I'm like, I liked astronomy in high school. I'll just start with that major, and if I don't like it, I'll change. And I stuck with it. And then I applied to grad school for both physics and for astrophysics, and I didn't get into any of the astrophysics programs. So here we are. I really big change, but it was really interesting. And I'm like, if I can't get into any astrophysics, the thing in physics that I really like is just magnetism. I found really interesting. So I kind of want to study materials if that's where I go, and that's how I kind of ended up here.
Great story. In fact, astrophysics is not that far from materials physics because all matter, in a sense, was synthesized inside the stars,
Mm-hmm.
in fact. Now, I explained a bit about this experience we had at the Air Force lab when we were performing this neutron scattering, and you and I were talking about the project all the time when I was in Dayton, Ohio. During that meeting, in fact, I met a scientist whom I knew for quite some time, Michael Sussner from the Air Force Research Lab. And it was sometime, in fact, after that meeting that I realized it's possible to send graduate students to the Air Force Lab for internship. And I, in fact, contacted Michael, and he kindly told me yes, he's very open to such a possibility if there's a graduate students who wants to go to the Air Force Lab in Dayton, Ohio. And I suggested that you do that. And again, we had to write another proposal to National Science Foundation, and it had its own challenges, but we eventually pushed it through, and it basically funded your trip to the Air Force Lab as a graduate student working in an Army lab, which is focused on fabrication of materials, specifically magnetic materials and devices. Could you tell our audience about that experience of going to this national lab and working there during the summer?
Sure, it was a really big change because military labs just kind of fall into this weird middle ground between academia and industry. So they're just kind of researching almost like academic scientists, but they usually have a much more focused on applications. Like they need a little bit more justification for everything that they make leading to something. But it was really cool seeing just so much space just devoted to research in all of these labs. Every measurement that I could imagine being able to take place in house, pretty much. Obviously, anything like a big beam or any like big labs they still had to go to, but like anything that you could reasonably do in a random building, they could do. And that was just really interesting. And just the vibe is very different when you have like these people, because it doesn't really feel like a normal job when you're on a university. Obviously, the professors are teaching and then they're helping you, and then they also have weird hours. And when you're a grad student, you have weird hours. So it's really interesting to have kind of that 9 to 5 flow, which makes it feel much more like an actual career you can have. Because when you're in grad school, it just kind of feels like this isn't what your entire career is going to be, and then to see that like all these skills still apply and they do lead somewhere, and like everything I've been doing in grad school has a real application in sciences in a normal job. It was cool to see.
Interesting. And maybe let's talk a bit about the future. Of course, you still have some time left to finish your doctoral dissertation. But generally speaking, after the experience of publishing now two papers and working on multiple projects and still having things to do and going to the Air Force lab and having this experience between academia and industry, after all of that, what is your thinking about future, about science, both for yourself and maybe if you talk to younger graduate students, what advice would you like to give them, or what do you have to tell them first on your end, and maybe then something for the younger students?
On my end, it's hard to say. I kind of just have gone forward. Like I said, I just kind of ended up doing physics and material science, and I liked it. And I'm certain whatever job I end up with, I don't exactly know what I want to do with the future, but I'll figure it out in the next year or so. I do want to keep doing some more research, so I know that very, very much. It's my favorite thing of what I do here. As for grad students who are maybe early in their career, I can't think of any great advice. Just it's really important to get as involved in the lab as you can. Ask people about stuff, even if it's not directly related to your project. I think I've had a lot of invaluable conversations just by asking people around the lab, like, "Hey, what you doing? What are you up to? Like, what are you working on?" And you just get introduced to a lot of techniques that maybe don't apply to your project, but are useful to know when you're talking to collaborators that you can do it, and to know what you might be interested in the future. Because I think I have found areas of material science in the past like year that I find very interesting, that I didn't really feel that way for the first like 3 years. I was kind of just going, it was a new field entirely to me, so I was kind of just going with what we were doing. I didn't know what exactly in the field really interested me, and having discussed things with more people and read more papers and making it a point to read more papers more often, I've kind of found those subfields of material science that I think would be interesting in the future.
Yeah, I certainly echo what you're saying, especially for younger students. Usually in the beginning, especially in doctoral programs, it's hard to grasp all aspects of what you do. But in my experience, usually once the students make some progress with their projects and they have a deeper understanding of what they do, that's where you see those real sparks of enthusiasm and excitement in them. And the more they take control of their own projects and pursue their ideas, it seems to me the more excited they become. So something for me to keep in mind. Thank you, Kyle, for this conversation. Congratulations again for
Thank
the
you.
wonderful work you've done. This work, as I said, is an editor's suggestion published in Physical Review Materials, Topological Hall effect induced by chiral fluctuations in erbium manganese 6 Kyle is still a PhD student in our lab, in the Tafti lab, but now he's a senior student and he's continuing with other exciting projects. And I hope that we'll have another conversation in the near future.
That'd be great.